now that we have analyzed the turbine, let's now just proceed in a clockwise fashion and focus on analyzing the condenser. Okay, so we'll move on to the step that involves going from stream 3 to stream 4, where we deal with the condenser. Okay, and so to proceed here, we're just going to go through our different balances. From the material balance, it's going to be basically the same thing that we got with the turbine. Inputs equal to output. That means M3 is equal to M4. And in the turbine, we figured out what M3 is. So that means we know what M4 is. It's just going to be equal to the 8.14 kilograms per second. In the energy balance, we'll write the open system energy balance. That's Q dot plus WS. And then we have the enthalpy going into the system and the enthalpy going out. Left-hand side goes away because it's steady state, no shaft work. And so what we find is that the heat, which in this case is going to be, if we go back to the diagram, going to be the QC of the Rankine cycle. So the heat that's leaving, that QC is just going to be equal, if we simplify it down, just to m dot multiplied by H4 minus H3. Okay. So at this point, we know what m dot is based on our turbine analysis. And we actually already have H3 as well from our turbine analysis. And so the only thing we need in order to calculate Q dot or QC is we need our H4 value. Okay? And so with stream 4, it's operating isobarically, so we know what the pressure is. And then our other assumption is that with a condenser, the outlet steam is going to be a saturated liquid, right? That's one of the assumptions we made, is a saturated liquid. And so we have our two pieces of thermodynamic information, the pressure and the fact that it's saturated. Okay, so based on that, one can just go to the steam tables and get all of the other information for stream 4. Okay, so I'll just write down a summary of all that information. We already know the saturation temperature at a pressure of 20 kilopascals. And then now, because it's a pure saturated liquid, we know that the enthalpy is just going to be equal to the saturated liquid value. And the same thing with the entropy as well. Kilojoule, kilogram, Kelvin. Okay, and so we have all the information we need to calculate QC, 0.14 multiplied by the difference between 251.4 minus the 2219.8 kilojoules per kilogram. And we get that the heat leaving the condenser and leaving the entire Rankine cycle is about negative 1.6 e to the 3 kilowatts. Okay, all right. So we have our value for QC, and we were able to get that through the energy balance. But equivalently, we could actually also get QC by doing the entropy balance as well. So to show you how that works, we just write our open system entropy balance. Okay. All right, steady state. And because we're assuming this process operates optimally and reversibly, And Sgen would also be 0 as well. All right, and if we go through the analysis, we know that M3, M4 are just equal to M dot, and really all we want to solve for is QC now. So QC should just be equal to TC times M dot multiplied by S4 minus S3. Okay, and if you plug in, what you get is negative 1.6 e to the 3 kilowatts. So we get the same answer, or you should get the same answer as the energy balance. And so really, this calculation, you could use it as a sanity check to just double check your answer. Okay. All right, in any case, we've now estimated what the heat leaving the system is. And once again, we could go back to our table and fill in the missing information. 1.40, 0.8320, and then here, negative 1.6 e to the 3, negative 1.6 e to the 3. Okay, and so that's how you do the analysis on the condenser portion of the Rankine cycle.